All right, we got a couple of easy type examples here where we're just dealing with operations of vectors, adding and subtracting. Notice that you're just adding the components like you do with complex numbers. Um, so here we go. If we're going to add v plus w, part A here, we're literally taking the first two parts, 7i plus 4i plus 3j plus a negative 5j, and I'm just going to keep that plus a negative, right? When you're done, you're going to end up with 11i plus a negative, so in this case, this ends up being minus 2j. Part B says subtract, so now we're literally taking the v, 7i minus 4i plus 3j minus a negative 5j, so minus the negative, right? This becomes 3i, and we're end up with a plus, negative is plus, is 8j. So that's addition and subtraction. Don't make that harder than it has to be. Scalar multiplication just means you're going to multiply through by some k. It's going to get longer, right? So if I have a vector 7i plus 10j and I multiply it by 8, I'm literally going 8 times 7i plus 8 times 10j. This is part A. And this gives me 56i plus 80j. Part B says we're going to multiply by a negative 5, so that's negative 5 times 7i plus a negative 5 times 10j, negative 35i minus 50j. And again, those are pretty straightforward. Okay, now is when it gets a little bit more difficult in that our problem now says we're going to multiply and subtract. So the question is, how do you want to do this? Do you want to multiply first and then subtract, or can we do it all at once? In other words, I'm going to take and multiply this whole thing by 6, and I'm going to multiply this whole thing by negative 3, right? That negative 3 allows me then to add. That negative 3 takes care of the subtraction. So this becomes, if you will, 42i plus 18j minus 12i plus 15j. And we can collect like terms pretty easily. 42 minus 12 is 30i. 18 plus 15 is plus 33j. All right. So again, pretty straightforward. Start getting into some things that are going to be a little more fun, I think. The zero vector clearly is just 0, 0. Nothing all that big there. It doesn't represent anything really, right? I'm going to let you stop the video if you need to and take a look at the properties here. These are the properties of vector addition and multiplication. These are the things that hold true, commutative, associative. Notice that the distributive property does work, things like that. The magnitude property, that's something new. The magnitude, remember, that's just a scalar times a vector. All right, so finding the unit vector that has the same direction as a given non-zero vector. Now, the reason we want that is that that unit vector will give us a direction. But it's going to have a length of 1. So when you multiply something by 1, it's not going to change the speed or the length of it, but because that has a direction to it, it will have an effect on the direction. So the unit vector is just literally the vector divided by its magnitude. Vector divided by its magnitude. Okay, find the unit vector. Well, first let's find the magnitude, which is the square root of 4 squared plus negative 3 squared. 16 plus 9, square root of 25 is 5. The unit vector is equal to 4i minus 3j divided by 5. You could leave it like that. You might want to go 4/5 I minus 3/5 j. Both of them will work, and that literally is a unit vector. Now, just to prove that, let's find the magnitude of that unit vector. So in other words, I've got this, and we're going to find the magnitude of that, which is going to be the square root of 4/5 squared plus negative 3/5 squared, which is square root of 16/25. That's a 16, trust me. Plus 9/25, which is equal to the square root of 25/25, which we know is 1. Okay, we now want to change directions here. We want to write the vector in terms of a magnitude and a direction. If you look at it carefully, doesn't this remind you of the polar coordinates? Good. Because this is going to be a lot like that, you guys. So magnitude and direction is what we're thinking. You've got your magnitude, you've got your direction in terms of your i's and j's, right? So let's jump into this and say the jet stream blowing at 60 miles per hour in a direction north 45 degrees east, express its velocity as a vector v in terms of I and j. All right, so we know that we have a magnitude of the vector that is going to equal 60. We have a direction here. Now, again, our direction says we are north east right here. That's 45 degrees in that rotation. If I look at it from this standpoint, though, that's a 45-degree angle here. Now, be careful. Turns out to be the same idea, same number, but a direction doesn't always necessarily mean the angle that we're having to work with. So theta is equal to 45 degrees here. So remember, our formula says our vector is equal to magnitude cosine I, magnitude cosine j. So we're going to go v is equal to 60 cosine 45i plus 60 sine 45j, and there's our vector. But we want it in terms of a component form, so we need to go ahead and simplify this. 60 times root 2 over 2 I plus 60 times root 2 over 2 j, or 30 root 2 I plus 30 root 2 j.